Okay, today we're going to look at how derivatives affect the shape of a graph. First thing we're going to look at is what first derivative can tell us about increasing or decreasing. So we know if your first derivative is positive, meaning greater than 0, then your line is going to have positive slope, and so it would be increasing. Similar, if your slope or derivative is negative number, less than 0, then you know any negative slope is going to be a decreasing line. So derivative in this area would be negative, less than 0. Derivatives in this region and this region have positive slope, so you should get a positive value. Okay, so in this example, we're going to look at where this function's increasing and decreasing. So first thing we're going to do on this problem is find the derivative. So derivative of this would be using our power rule 12x cubed minus 12x squared minus 24x, and derivative of 5, which is a constant, would be 0. So next thing we want to do on this to figure out where it's increasing, decreasing, is see where is this going to actually equal 0. That would give us our places where it's going to change direction. So here it appears we can do some factoring. Let's factor out the greatest common factor of 12x. That would leave x squared minus x minus 2. Doing a little bit more factoring here. Factors of x minus 2 and x minus, plus 1. And now setting all those equal to 0, we would get 0, 2, and negative 1. So those are the places where this possibly changes direction, where the derivative equals 0, are critical numbers. So now the next thing what we want to do to figure out where it's increasing, decreasing is, like we've done in the past, look at those spots, so negative 1, 0, and 2, and see what's happening on the intervals in between those. So what we can do is test those out with our factors here. So let's pick a number bigger than 2 to start with. So if we were to put, say, the number 3 in for these x's right here, what's going to happen? Well, if we put 3 in this first one, we're going to get a positive value. If we put 3 in for that middle one, 3 minus 2 is 1, that's a positive value. 3 plus 1 is also a positive value. If we multiply 3 positives, this is going to come out to be a positive slope, or increasing. Okay, now let's pick a number in between 2 and 0, like 1, and see what happens at 1. Well, at 1, this will be positive. 1 minus 2, though, now that's negative. 1 plus 1 is 2, that's a positive number. If we multiply 2 positives and a negative, there's going to be a negative value there, or decreasing slope. All right, now let's pick a number between 0 and negative 1. Here we don't have any integers or whole numbers to deal with, so let's do like negative 1/2. If we did negative 1/2 times 12, that's negative. Negative half minus 2, that's negative. Negative 1/2 plus 1, that's still going to be positive half. And so if we multiply 2 negatives and a positive, negative times a negative is a positive, so that's going to be positive slope in there. All right, finally, we got to test numbers less than negative 1. Let's try like negative 2. So if we put negative 2 in there, first one's negative, second one would be negative, last one's also negative now. 3 negative numbers multiplied is going to result in a negative value. So now we know where this is increasing and decreasing. We would say it would be increasing on the intervals from negative 1 to 0, and also 2 on, so 2 to infinity. This would be decreasing on the intervals from negative infinity to negative 1, and also 0 to 2. So that would be the places we now know it's going to be positive and negative. Okay, first derivative test. If we have a critical number like we did in the last problem, if f changes from positive to negative, then it's going to have a local maximum. If the derivative changes from negative to positive, then it's a local minimum. If it does not change signs, like it stays positive on both sides of the critical number, then it does not have a maximum or minimum at that value. So this shows, here's some pictures to show that if you got positive slope into negative slope, that means this would have to be a high point. That would be a local maximum. If you got decreasing into increasing, then it's going to be a minimum point at that value. If you have the same, so it's positive, you get a slope of 0, but positive again, this point does not end up being either a maximum or a minimum then. So it does have to change directions. Similar, if it's negative into negative, this point's also not a max or min. So we can go back to that last problem and use this to figure out what kind of points these are going to be. For example, at -1, we had decreasing slope into increasing slope. So what kind of point is -1 going to be? Local minimum. At 0, we got increasing slope and a decreasing slope. So 0 is a local max. At 2, decreasing and an increasing slope. So this one is another local min. So first derivative test can help you determine if things are minimums or maximums. All right, so in this example, they want us to find the local maximum and minimum values of this function on the interval from 0 to 2 pi. So like the last problem, our first step, we'll figure out what is the derivative of this. So derivative of x is 1. Derivative of 2 sine x, 2 is just a coefficient here, so we can bring that with. Derivative of sine is cosine. Okay, now like the last problem, we want to set this derivative equal to 0 to figure out the critical numbers. So to solve this, let's subtract 1. Let's now divide by 2. So now we got, where's cosine x going to be equal to -half? To find one of those values, we could do inverse cosine of this to figure out. Now, you could use this, do this on the calculator, or if you remember back from unit circle, that cosine's your x values. You could also figure it out with some of those special right triangles. All right, so let's put this one in and see what we get. So if we do inverse cosine of -1/2, got the negative here, -0.5. We get this value. Now remember, these numbers should be in radians here. So if we divide out the pi, we should see what's left here. So let's divide out the pi value. And we get 0.6666 repeating, which as a fraction is 2/3. And so we know that one possible value here is 2 pi over 3. But this is on the interval from 0 to 2 pi, so we want to figure out, is there any other values here? Well, this is remember cosine is a x value, and it's negative. So which quadrants would have negative x values? The second quadrant, but also the third quadrant. So we know that 2 pi over 3 produces one value. We want to find that same value in the third quadrant. So that would be the same as going -2 pi over 3 in that direction. To get that between 0 and 2 pi, though, what we'd want to do is add 2 pi to that. So what is -2 pi over 3? In between 0 and 2 pi, we'd want to add 2 pi to that. If we get a common denominator here by multiplying by 3 over 3, that's going to turn into -2 pi over 3 plus 6 pi over 3. And so adding that up, that would be 4 pi over 3. So the two locations here in between 0 and 2 pi that we'd want to check would be 2 pi over 3 and 4 pi over 3. All right, so now to figure out if they're maximum or minimum values, we want to check numbers in between. So we got our first derivative here. The values we're checking, 2 pi over 3 and 4 pi over 3. So we want to see what's happening in between and outside of those values. A number we could pick that would be less than that would be, say, 0 would be less than that. So what if we put 0 in for our derivative here? What kind of value are we going to get? Is it going to be positive or negative? So let's try, let's see what we get. We put 0 and we get 1 plus 2 cosine 0. We know cosine 0 is 1, so this comes out to be positive 3. So in this region, we get a positive slope. Let's pick a number in between 2 pi over 3 and 4 pi over 3. 3 pi over 3 would be a number we could check in between, which is just the same as pi. So let's check what this would be at pi. So similar, if we do 1 plus 2 cosine of pi, we get negative 1. So in this region, the slope is negative or decreasing. Let's do one more. Let's check a number bigger than 4 pi over 3. 2 pi would definitely be bigger than that. So let's check it out. What do we get when we put in 2 pi? So if we do 1 plus 2 cosine 2 pi, we should know what this one already is because 2 pi is the same as 0. So it should give us the same value as before, but just to show it, this does give us positive 3, and so this would also be increasing here. So now to determine maximum and minimum values, look at the slope. If we have increasing into decreasing, that tells us that this would be a local maximum point. If we do decreasing into increasing, this is going to be a local minimum point. And so that's the values we get there. All right, next one, find where the function is increasing, decreasing, and any local max. So now they want us to do both, find the increasing, decreasing, and also the maximum and minimum value. So first thing, again, find the derivative. So derivative here, derivative 2 is a constant, that's 0. Derivative of the next one would be 4x. Derivative of the next term would be 4x cubed. Now we want to set that equal to 0. It looks like there's a greatest common factor of 4x that we can factor out. This factors further here. This would factor into 1 minus x and 1 plus x. Now setting all those equals 0, the places we get would be 0, 1, and negative 1. What I want you to do, pause the video now and see if you can figure out what the slopes are going to be inside those values, in between them, and outside of those values. So for our first derivative here, what kind of values do we get outside and in between those? All right, let's check and see how you did. If you pick a number bigger, like let's say 2 here, 2 would make this positive, this negative, this positive, so this is going to be a negative slope out here. If you picked a number in between 0 and 1, like a half, you're going to get positive. This would be positive. This would be positive. They're all positive, so that's positive slope. If you pick a number like negative half, now things change a little bit. This first number is going to be negative here. Negative half, though, minus a negative is actually positive, and 1 plus negative a half is still slightly positive. So this should be a negative slope. If you put a number like negative 2 in there, now the first one's negative. Also, the last one would also be negative. And if you multiply 2 negatives and a positive, you get positive slope. So that should have been the positive negatives. So now they do want us to say the intervals here. So we would say it'd be increasing on the intervals from negative infinity to negative 1, and also 0 to 1. This one's decreasing on the intervals from negative 1 to 0, and 1 on. And then last thing they want us to figure out is what are the local max and min. So now we should be able to say those local maximums would be any place where it changes from positive to positive slope to negative slope, which would be at x equals -1, and also at x equals or -1 and x equals +1, because both of those are changing from increasing to decreasing. This also has a local minimum where it changes from decreasing to increasing, so at x equals 0. Okay, the next thing we're going to look at is what's called the concavity of a graph, and that's kind of how much the graph curves or what kind of curvature it has to it. So if a graph lies above all its tangent lines on that interval, then it's said to be concave upward. This is an example right here of a graph that's concave up. Because if I draw the tangent lines, the places where the lines hit the line one time, you can see all the tangent lines are below the graph. So this curvature you see in this example is concave up. The second one is one that's an example of concave down. And concave down lines have all its tangents above the line. So if I draw on the tangent lines here, where the line hits the graph at one point, they all lie above the graph. So that's an example of a curvature of concave down. On this graph, they want us to show where this is concave up and concave down. So we're trying to figure out where does the graph have that kind of downward curvature or upward curvature. So to start out with, this graph here, all the tangent lines would be above. All this is concave down. It's all curving downward. Somewhere in here though, it changes now. This is concave down. But now our graph starts curving up. It has that upward curvature where all the tangent lines would be below. So in this region, we would say it's concave up. Now somewhere in here again, it changes. This goes back to having tangent lines above, so this would be concave down in here. Now we have this upward facing curvature again, so everything in here would be concave up. Here, now there's like a little point here, but this still has this upward facing curvature, so it's still concave up in here. But now again, somewhere in this region, the tangent lines start going back above it, so this would be concave down again in this region. Okay, now when these change from concave up to concave down, we do have a word for those points. Those are called inflection points. So any place where your concavity changes is called an inflection point. And those points can tell us things about the graph, as we'll see in some examples coming up. So in this example, when we were looking for these, this would be an inflection point right here, somewhere around that location. This would be an inflection point. Here we're changing, and then here would be an inflection point. So anywhere you switch from concave up to concave down, inflection points. Now there is a test to see if something is concave up or concave down with the function. And what we do is we just check the second derivative. So the second derivative of a function, where that's greater than 0 or positive, then the graph is concave up. If your second derivative is less than 0 or a negative number, then it's concave down. To help remember this, you can use the little Mr. Smiley, Mr. Frowny test. And so if you get something that has a positive number, meaning bigger than 0 here, positive number, then it's going to have the concave up smiley face curvature to it. If you get a second derivative that's negative, then you get this downward Mr. Frowny curvature to it. So think of Mr. Smiley, Mr. Frowny when you want to figure out concavity. Positive is concave up, negative concave down, like a frowny face. Okay, this example here shows the population of the Cyprian honeybees raised in an apiary. Apiary is a place where they raise bees. How does the rate of the population increase over time? When is this rate highest? Over what intervals is P concave up or concave down? So they got a bunch of questions for us to ask. So right away, this type of curvature in here you've seen before. This part of it looks like, and I kind of went off the graph here, but this is the exponential, increasing exponentially that you guys have seen in the past. However, somewhere around this point, right around 12, the curve doesn't keep increasing exponentially anymore. It starts kind of slowing down or decreasing. And if you keep going and look at stuff with like biology and that kind of stuff, there's something called carrying capacity. And what that talks about is things can't keep increasing exponentially forever in realistic situations. There can't be exponential amount of bees because the environment that the bees live in can't support that many infinite bees. And so there's some value that the bees can't really increase above because there's not enough resources for that many bees to live. So as that exponential graph keeps increasing, sooner or later it's going to slow down, and the number of bees here are going to start approaching that carrying capacity because there's not enough resources for it to live. And so to answer some of these questions, how does the population increase over time? Well, right away it increases exponentially, and then it starts going towards its carrying capacity. When is the rate the highest? Well, the bees are increasing the most at this point right here, because that's when it had the greatest slope. Then the slope starts changing and it starts decreasing. And that point would be our inflection point, actually. The inflection point does tell you the highest rate of change. And so somewhere around 12 weeks here, because you can follow it down, somewhere around 12 weeks is when it's going to increase the highest. Over what intervals is P concave up and concave down? Well, here you can kind of see in this green section, this was concave up because we were starting to increase very fast, exponentially. This red section over here now, since we had an inflection point, that's where it's concave down because we're approaching that carrying capacity. It's not increasing as fast. Still increasing. This whole graph is increasing. It's just the rate of change of the increase is changing. And that's what concavity is. The rate of change of your increasing or decreasing. All right. Here they want us to do a sketch using some of the information given. So here you got to take what they're giving you and try to sketch out and have a graph that shows what's being said here. All right, so first thing here, let's maybe start with something we're familiar with. You guys have seen these limits before. So here it says the limit as we go to negative infinity approaches -2. So remember, this would mean towards the left. So on the graph here, as we move out towards the left, our graph should be approaching -2. Now, we don't really know, is it coming from above here or is it coming from down low? We might have to change this later. These ones are good to do in pencil because you're probably going to have to do some erasing or changing. Also, we know as it goes to infinity to the right, we're going to be approaching 0. Again, I don't know if it's going to be coming from the top or bottom here, but let's kind of sketch it in for now. We can always change it if we need to. All right. Now let's go to the next stuff we know about this. These next ones are saying our first derivative is greater than 0 from -infinity to 1. That means greater than 0, positive. So our slope, our first derivative, our slope's increasing from -infinity to +1. So it looks like my graph down here already kind of has positive slope. It's going to keep increasing till it hits positive 1. At positive 1, though, now our slope is going to be less than 0, or a negative number from 1 to infinity. So here, looks like there's probably going to be some kind of maximum at 1, and then start decreasing here. So we want to try to show, on my graph, maybe fix a little bit. At 1 here, there's going to be a maximum. All right. So now our graph has all those. Now the next stuff is dealing with second derivative. So now this is starting to talk about the curvature. So the second derivative is greater than 0 from negative infinity to negative 2. Greater than 0 is positive. So positive value, using our Mr. Smiley here, we should have concave up. So from negative infinity to negative 2, it should be concave up. And I think we already kind of have that curvature here. So it's concave up to right here. At negative 2, though, now it looks like it's changing. Negative 2 to 2, our second derivative is less than 0. It's a negative value. So negative value, now we need concave down like our Mr. Frowny. So I'm going to have to erase right here. I want this now to be concave down here. So it switches from concave up to concave down. And it stays concave down all the way to positive 2, which should look like the curvature we want here, because this is a maximum. So it stays concave down till 2. So at this point, and this point now, we know are probably inflection points because they're changing. Okay, and then from negative infinity, that should be, or sorry. Yeah, that was right. And then from 2 to infinity, it's also concave up. So now it switches back to concave up. So it should have more of this curvature. So we also know that this would be a local max. So now this graph is a rough sketch. Now it might go higher, lower. I don't know if this is exactly right, but this would be the sketch, at least with the curvature, is correct with all the stuff that it says here. So this would give you full credit on one of these type of sketch drawings. All right, last thing, second derivative test. If you know that something has a local or a critical value where its derivative equals 0, if you test that value with the second derivative, then you can tell if something has a local max or min at that value. If at a critical value the second derivative produces a positive number, it's going to have a local minimum. And the reason is, think about, what do you know if second derivative is positive? It's Mr. Smiley. Well, think about, if it's smiling, what kind of point is this going to be? A local min. If your second derivative produces a negative number, that's our Mr. Frowny. Think about, what type of point would this be? A local max, like it says here. So testing out a critical value with the second derivative tells you if it's local min or local max by what kind of point you would have based on the curvature. Okay, so we can use that, and we'll use that on this last problem. So this last one, this is that one we had, I think, looked at before. They want us to now use it to sketch out, or look at the inflection points, local max and local min, and that kind of stuff. So like we did earlier, I think, with this problem, if this was the same one, I want to say it was. Oh, maybe it was not. All right, well, let's go through that and look at this one. So we are going to find out all the stuff about this. So first off, let's look at first derivative, which would be 4x cubed minus 12x squared. Setting that equal to 0 will give us the critical points. So it appears we can do some factoring here. Let's factor out a greatest common factor of 4x, leaving x squared minus 3x here. Oh, sorry, we can factor out x squared. Let's do 4x squared. leaving x minus 3 here. So on this one, the two places that this would equal 0, if we put both these equal to 0, would be at 0 and at 3. So with our first derivative, we want to check what's happening inside and outside of those points there. So to the left, or to the right, if we tried like 4, both of these are gonna come out to be positive. If we tried, say 1, this would be negative. This would be positive, so this is gonna be negative. Now you got to be careful about these ones. A lot of the graphs so far, they've kind of alternated. Don't assume though that this is going to be positive, because in this case it actually isn't. Watch what happens when we check, like say -1 here. -1 would make this term on the right still negative. If we put -1 in there though, -1 squared is +1. +1 times 4 is +4. This is still positive. If we multiply positive and negative, that area, or that region, is also going to be decreasing slope. So that's where you got to be careful about testing some of these. Make sure you actually go through it and test. All right, so now we know based off of this where it's increasing, decreasing, etc. Now let's look at second derivative. Second derivative of this graph, going off of this first derivative, would be 12x squared minus 24x. Let's find the inflection points by putting that equal to 0. So if we set this equal to 0 and factor, we'll get that at 0 and at 2, we got possible inflection points. So let's also make a graph here. Let's look at second derivative and see what kind of concavity we're going to have here. So if we do a similar thing now and test some points, let's say we put in 3, that's positive there, because 3 will produce 2 positive numbers. If we put in 1, this would be positive, but that's negative, so that's a negative value there. If we put in, say, -1, both of these are going to come out to be negative, which means that's positive. So now we know some stuff about the concavity. In this area where it's positive, that's going to be concave up. Negative is concave down. Positive is concave up, Mr. Smiley. So we know the curvature on all these points for these. We could also use this second derivative if we wanted to test to see what kind of points 0 and 3 are using that second derivative test. So that second derivative test could let us test, say, and see what kind of point 3 is. So what would the second derivative be at 3? If we were to plug 3 in, we'd get 12 times 3 squared minus 24 times 3. That would give us a value of, doing that on the calculator quick, would give us a value of 36. That's a positive value, so that means concavity is positive. So what kind of point is that going to be? This tells us it's a local minimum at 3. And we could also tell that from our first derivative test. If we got decreasing slope into increasing slope, that also tells us 3 is a local minimum. So the second derivative test could tell you. Now also, if you did second derivative at our other critical point of 0 though, and plugged 0 in for our second derivative at those 2 points, that would actually equal 0. Well, that's not positive or negative, so that means there's not a local min or max at 0, and that should be true. Look at both sides of 0 over here. We got decreasing and then decreasing again. That's not a local min or max point at 0. So now last step, they want us to kind of sketch out this curve. So we got all the information. Let's sketch it out. So our important points that we want to make sure are on there would be at 0 here, at 2, and at 3. Those are where the important information is going. So it's decreasing to 0. It levels out at 0 because our we do have a critical point there, but then it keeps decreasing until we hit 3, and then it's increasing. Now let's adjust this with our slope here, or our curvature. From negative infinity to 0, it's concave up. So we want to make sure this is concave up here. When we hit 0, though, now from 0 to 2, it's concave down. So let's change our graph a little bit here. Concave down. And then from 2 to 2 on, it goes back to concave up. And so our graph should look something like that, with 3 being a local minimum there. So that's roughly the shape of this graph. It's not exact, but roughly the shape of that one. Okay, you're going to try now some problems out on your own with these graph with derivatives and second derivatives.